Hello, good morning to all of you. I hope all of you are doing well. So today we'll start with our fourth objective, that is to divide one hexadecimal number by another hexadecimal number using successive subtraction. Now here the registers that are used are A, B and C, and the location where the results are stored are F000H and F001H. So F000H stores the remainder, F001H stores the quotient. Okay, so the starting location of the program is C000H. Now let us have a very simple explanation about the program in hand or the problem in hand. So you have A, B and C, the variables that are participating in realizing the program. So A is the dividend that and the value it's holding is 10 hex. So 10 hex in decimal is equivalent to 16. Now B is holding the divisor and C is holding the count. So B is holding 5 and C is starting from 0. So now let us start the subtraction process. So now first time B is subtracted from A. Okay, so 5 is subtracted from 10, so the resulting value will be 0b and the count is incremented by 1. Next time 5 is subtracted from 0b, we have 06, count will be 2. Okay, next time 5 is subtracted from 06, we have 01, count will be 3. Next time whenever 5 will be subtracted from 01, we'll have -4 and count as 4, but here the borrow flag will be set. As in the previous class, as I've said, in case of subtraction, if the value cannot be accommodated, borrow flag will be set. And in case of addition, if the value expands, then carry flag will be set. But in case of 8085, the same flag will be representing borrow as well as carry. So borrow in case of subtraction and carry in case of addition. So now here the value of A has become -4, value of C has become 4. So now what we need to do is, since the borrow flag is set, the subtraction process is to be stopped and the value of A and C is to be adjusted. So now A is -4, so -4 plus 5 is equals to 1. So now this will be the remainder, and 4 minus 1 is equals to 3. This will be the question. So we need to readjust the value of A and C. So let us transform this particular explanation into concept note and a program using 8085 instructions, right? So here what we have is we have the concept node. So A is equals to 10 hex, B is equals to 05 hex, C is equals to 00 hex. Okay, so now here what we have is we have the iteration. So we are successively subtracting B from A, and every time subtraction is being done, value of C is incremented by 1. So the process repeats until unless the borrow flag is not set. So once the borrow flag is set, then the value of A is to be adjusted. So A is equals to A plus B, that is -4 plus 1 is equals to 1, that will be the remainder. So once the value of A is adjusted, then what we need to do is we need to store the remainder in F000H. Then again value of C has to be adjusted because C was incremented one more time. So C minus minus, so decrement the value of C by 1. Then move C to A, right? Copy the content of C to A and again store the result in F000H. Now why we are moving the content of C to A and why we cannot move the content of C directly to memory location is because, as I previously said, that any of the operation that you want to perform, A should be one of the default operands. So any value that you want to store in computer's memory has to be brought to A and then it has to be stored, right? So likewise, we have the equivalent representation of the concept using instruction 8085 instruction set. So MVI A comma 10H, MVI B comma 05H, MVI C comma 00H. Then we have the iteration. So here now just see, we have used the instruction J and C. So in case of subtraction, J and C will work as borrow. It will check the borrow flag. Okay. In case of addition, it will check the carry flag. So we are successively subtracting B from A, and every time subtraction is being performed, we are incrementing the value of C by 1, right? Then eventually, once the borrow flag is set, the value of A is adjusted by adding the value of B to A. Then the result is stored in F000H, which will keep track of the remainder. Then C is decremented by 1 because value of C also has to be adjusted because C was incremented one additional time. Then move A to C. Now just see, this instruction moves the content of register C to register A. Okay, right? Now Then store the content of A in F001. That will keep track of the number of subtraction that has been done. So HLT halt eventually, right? So now this is the opcode for the program 3E10060550E00. Then we have a label for creating iteration. Then we have 900C C2L1. So now this representation of label L1 will be replaced by the absolute address in case whenever you're placing it in the computer's memory. Then we have add B, that's A0, then 32 for STA, then 00F0, as I've already said, higher byte in higher address space and lower byte in lower address space. Then we have DCRC, that is 0D, then move A comma C 79, then 3201F0 76. So now what we need to do is we need to store this particular program in computer's memory. So C triple 0 we have 3E, 01 we have 06, 02 we have 06, 03 we have 05, 04 we have 0E, 05 we have 00, 06 we have 90, 07 we have 0C, 08 we have C2, 09. Now this label L1 has to be replaced with the absolute address. So in 09 we have 06 and 08 we have C0. So C006, because C006 is the address of the instruction that's pointed to by the label, that is subtract B, right? So likewise in C at C00B we have 80, at 0C we have 32, 0D we have 00, 0E we have F0, 0F we have 0D, 10 we have 79, 11 we have 32, 12 we have 01, 13 we have F0, and 14 we have 76. So this is the way how successive subtraction is used in order to realize division operation. Now let us come to our next objective. That is a very simple objective. That is to add the sequence of FF and 01 thrice to the content of the accumulator and keep track of the carry. Okay. So now here the registers that are used are A, B, C, D, and E. So location where the results are stored are F000H. So F000H will store the sum, whereas F001H will store the carry, and starting location of the program is C000H. Okay. So now here we have 5 operands participating: A, B, C, D, and E. Okay, that's right. So we have A, B, C, D, and E. Now A is the accumulator. B and C. B I have placed FF. At C I have placed 01. Okay, and E I'm keeping track of the using E I'm keeping track of the carry, and D is the number of times the addition is to be performed. So it has to be added 3 times. So the initial value of D is 3. Okay, now 0. So initially what I'll do is I'll add FF to A. So A is 00. So 00 plus FF makes FF with no carry. So carry count will be 0, right? Again. Now again 01 is added to FF. So whenever 01 is added to FF, A becomes 00, right? And there will be a carry. So carry count is incremented to 1. Okay. So sequence of FF and 01 is added. So now D becomes 2, right? Again, now 00 again 00 plus FF, so they will not be carry, so carry count remains 01. Now 01 is added to FF, so now there is a carry, so the result will be 00, and there is a carry, so carry count will become 2, right? Again, and once the second sequence of FF and 01 is added, so D becomes 01. So again FF is added to 00, right? And there is no increment in the carry count, so carry count remains 02. And 01 is added to FF. Now there is the value of A becomes 0, and there is a carry, so carry count becomes 3. So once the third sequence of FF and 00 is added to A, D becomes 0, right? So here the carry count is 3, D is 0, right? So what I need to do is I need to store this result. So the result of the addition operation to A will be eventually 0, right? And the carry count will be 0, 3. So let us realize this particular program using a concept node and equivalent 885 instruction set. So initially A is 00, B is FF, C is 01, D is 03, and E is 00. right? So here A is 0 0, B is FF, C is 0 1, D is 0 3, and E is 0 0, right? So now first what I'll do, I'll add B to A, right? I'll add B to A, then I'll add C to A. So if there is a carry, jump to label L2. So at label L2 what I have is I have incrementation done on E. So E plus plus if there is a carry. So if there is a carry, go to L2. So then increment the value of E, then go back to L3. So this is without any condition, okay, right? Okay, so go to L3. So what I'll do is I'll go to L3. So out of 3 sequence I've added 1 sequence, so I need to decrement the value of D by 1 here now, okay, right? So while D is not equals to 0, the process repeats, okay? So now the sequence of FF and 0 1 will add it 3 times to A, right? So once D becomes 0, then what I need to do is I need to go to L4, because you know that the labels will be sequentially executed whenever a label is written in a program. So I want to avoid L2 to be executed one more time. So go to L4. So directly I'm transferring the control to L4. So I'm transferring the control to this particular location because I want to avoid extra execution of this particular label. So then what I'm doing is I'm storing the result into address location F000H. The first result is the remainder, and the second result is the carry count, right? So this is a very simple concept note representing the problem in hand. So A is initialized with 00H, B is initialized with FFH, C is initialized with 01H, D is initialized with 03H, and E is initialized with 00H, right? So now what I have is I have an iteration where I'm adding the value of B and C to A. So once there is a carry, there will be a jump to label L2 where the increment to the carry count will be done. Again, in order to repeat the process, I need to go back. So go back to label L3, then decrementation to the count is done, and the process repeats until unless D does not become 0, right? So once D becomes 0, we need to go to label L4. Why? Because we need to avoid execution of label L3 once more. So then we have to go straight to label L4. So label L4 is here. We will be storing the result in the desired address location. Right, so this is a very simple concept node. So now let us realize it using instruction set. So here A is initialized with 06, B is initialized with 05, C is initialized with 01, D is initialized with 03, and E is initialized with 00. So this is the carry count here, right? So now add B, add C, jump on carry to L2. So the label L2 is somewhere here where we increment the carry count, and again jump to L3. Again we will go back and decrement the value of D and jump on node 0 to L1 because the iteration is to be repeated. Once the iteration is over, then jump to L4. Straight away we'll come to L4 because we want to avoid extra execution of L2. So jump to L4. So where we'll be storing the result in the desired address location and eventually HLT halt. Right. Now this is the opcode for the SAID program. So 3E0006FF 0E01 1603 1E00 L1, then add B, that's 80, add C 81, DA is jump on carry to L2, right? Then we have label L3, so then we have 1 5, then C2 L1, then we have C3, that is jump, then we have L4, and then we have label L2, so 1C, C3, L3. Now we have label L4, then 3200 F0, 7B, 7201 F0, 76, right? So now what we need to do is we need to store this particular program into computer's memory. So the starting address is C000. So at C000 we'll have 3, subsequently 0606. 05, 0E, 01, 16, 03, 1E, 00, 8081. D1 is for sorry. So this is jump on carry. So we need to check the opcode for jump on carry. So just JC, then C00D, that is holding the representation of the label. So label is somewhat here. So what we need to do is we need to skip space as and when we need to carry we maintain the sequence of the address space. So we will leave two address locations for L2. So C00D and C00E as of now will be left for L2. Then we have L3. So L3, that is C00F, we have 15. Then we have at C010, this is C2, 11 we have 0A, then C0, C3, 1A, and C0. Now just see here, label L2, right, is somewhere here. So label L2 is somewhere here. So this is a forward jump. So from this particular location, we are making a forward jump to this particular location, right? Okay, so the address value of this particular location is C016. So now what we need to do is we need to store C016 here. So higher address in higher address byte in higher address space, lower address byte in lower address space. So this is the way how you need to manage the forward jump. Okay, so at C00D now we'll have 16, and C00E we'll have C0. So likewise at C017 we'll have C3, then label L3. So label L3 is somewhere here. So label L3 is somewhere here, and it's tagged with C00F. So C0F0 here, right? Again, C00F here, right? So now at C01A we'll have 32, and 1B will have 00, then 1C will have F0, right? So then we have 7B at 1E, 1D, then we have 32 at 1E, then 01 at 1F, F0 at 20, and then eventually 76. So this is a very simple program that enables one to learn how to create forward and backward jump. Okay, right? So whenever we are creating a forward jump, always remember keep 2 bytes open for that, right? Okay, so here initially keep C00D and C00E open for L2 whenever you are calculating the address. Okay, so this is a very simple program that tries to add sequence of FF and 01 to the content of accumulator and tries to keep track of the carry count. Okay, now likewise, the sixth objective or the next objective that we have is to swap two hexadecimal number stored in two specific address locations, right? So this is a very simple program, right? Now let us consider the registers that are used are A, B, and C, and the locations are F001H and F002H, okay? And the starting address of the program is C000H. Now here, so first what I need to do is, since I've already said that any operation that you want to perform has to have accumulator as one of the default operand. So here any data transfer that takes place should take place through A. So now first what we'll do is we'll place the content of F001H. So we'll place the value stored at F001H to accumulator A, right? Because anything that has to be used or that is supposed to be used is to be brought to A. So the content of F001 is put to A, then content of A is put to B, right? So now B will hold one of the operand, right? So likewise, once the value of A is been initialized to B, now value of next address location can be extracted. So value of F002 is stored in address location, is stored in the accumulator A, right? Now that content is again moved to C, right? So now B and C are holding two operands or two values that are to be swapped, right? So now what I'll do is I'll swap the content of B and C, right? So now A is equals to B, right? B is equals to C and C is equals to A. So this is a very simple logic for swapping the content of two variables, right? Okay. Again, what I'll do is I'll move the content of C to A, right? C to A, and it will be stored in the address location F001H. Then again I'll move the content of B to A, and it will be stored in the address location F002H. So this is a very simple program for adding for swapping two numbers. But here what we are doing is we are fetching the values first and then swapping it and eventually again putting it back to the address space. Now this can be run. This can be done using a very simple concept note as well. But just to make you understand, what I've done is I've used this particular concept note. So now first, let us transform the concept note into equivalent 8085 instruction. Now LDAX. Now LDAX is an instruction that is capable of loading the accumulator with the content of the address location. Okay, again I'll repeat it. LDAX is an instruction that is capable of loading the content, loading the accumulator with the content of the address location. Is it understood? So it's a very simple instruction that loads the accumulator with the content of the address location. So now what we are doing is once A is loaded with the address of the with the content of the address location, then we are moving A to B. Likewise, LDA. Sorry, it's not LDAX. So it's LDA. There is a mistake here. So this is LDA. Okay. So load the content. Load the accumulator with the content of the address location. So this is LDA. Please. Uh, don't get confused. Okay, so this is a typo error here. So now move b comma a, so move the content of accumulator to b. Likewise LDA f002, so load the content of the address location f002 to the accumulator. So now what we have done is initially we have loaded the accumulator with the content of f001 to A, then we have moved it to B. Likewise, we moved the content of f002 to A and we have moved it to C. Then what we have done is we have swapped the contents of A and B, right? Okay, so we have used equivalent instruction set. So C is equals to A, that is replaced by move C comma A. So we will move the content of A to C, then B to A, C to B, A to C, and so on and so forth, right? Okay, then eventually store the content of accumulator to the address specified. So then eventually what we'll do is just see after the swapping is over. After the swapping is over, then we move the content of C to A, right? Okay, and store the content of the accumulator to F001. Then likewise move B to A, then store the content of the accumulator to F002, and then eventually halt. So this is a very simple program. So here please don't get confused. It is LDA, it's not LDAX. Okay, there's a typo error here. So first load the accumulator with the content of B, content of the address location, move it to B. Then again load the accumulator with the content of the next address location and move it to C. Then swap the values of B and C. Again store the content of B and C through the accumulator to the desired address space. So now here what we have is we have the equivalent opcode. So 3A01F0 47, again 3A02F0, then again 4F, then 784145793201F0, 78, then 3202F0, and halt 76, right? So now what we need to do is we need to store these opcode and the data codes, the operation byte and data byte in the address space. So the starting address of the program is C000. So at C000 we have 3A. Likewise we have 01 F0 473A02 F0 47. Then we have 78. Then 41. Then 45. Then 78. Then 32 and 01, then F0, then 78, then 3202, then F0, then 76. Likewise, so what we have done is we have stored the program in the address space as well, right? So this is a very simple program that's capable of swapping two numbers. Now we'll call it a day. So we'll start with the next objective in the next class. So I hope it's clear to you. So please refer to the instruction table whenever you have to replace the instruction with the equivalent opcode. Okay. So thank you very much.